Hi, Calculus. We are going to do a couple more examples and then maybe take some notes for future. I don't really know. We're just going to see how this video goes. Um, we're going to start with the examples we didn't get to in class, specifically a couple more u substitution problems. And this first one is the antiderivative of sine times e to the cosine dx. Now, if you guys remember, we have to first pick a u, pick something whose derivative is in the problem, and we want to be mindful of the thing we pick should cancel something out. I say that because in my eyes, there's two options. We can pick sine or we can pick cosine. And I know the derivative of either of those is the other. Yes, there's a negative on one, but that's not really the piece here that's important. So the question is, which should I pick so that the derivative cancels? If I pick sine, my cosine won't cancel because it's e raised to the cosine. So I know my u needs to be cosine of x. That means the derivative of u is negative sine of x dx, and then we take the time to substitute all of our pieces in. So the integral of sine of x times e to the u du over negative sine of x. Our signs cancel, and we have this negative. I'm going to pull that out here. Negative antiderivative of e to the u du, which is just negative e to the u plus c. And we substitute back in our u, so negative e to the cosine of x plus c. Yay! Good job. I believe we have a couple other examples we want to do. And these are our 1 over u forms. So in these examples, notice we have a fraction, and we can't take an antiderivative of just a fraction, and we can't split it up either because the denominator has more than one term. So I look at this and I think, oh, well, I see that the derivative of the bottom is similar to the top. Maybe it's exactly, I can't even tell right away, so I'm going to just start there. U is equal to 3x squared minus 2x. That means du is equal to 6x minus 2. Hey, that's really nice. So this is the integral of 6x minus 2 over u times du over 6x minus 2, right? Because we solved for dx, move that to the other side. These little guys cancel, and we have the antiderivative of 1 over u du. If you remember, the integral of 1 over x, 1 over a number, is the natural log of that number. So we're looking at the natural log of the absolute value of, well, I guess I can do this in two steps. The natural log of u plus c, but of course the natural log of, we're going to substitute back in our u, our 3x squared minus 2x. For b, let's look at this one. We have secant squared over tangent. And I look at that, and the first thing I think is, well, I know the derivative of tangent is secant squared. And so I'm like, hey, that's good news. So let's pick u is tangent, du is secant squared. I substitute pieces in. Secant squared x over u times du over secant squared. Lovely. Antiderivative of 1 over u du is equal to the natural log of u plus c. And we got to plug back in our u, so we have the natural log of tangent of x plus c. Good job. Well, I actually don't know if you did any of those, but hopefully good job. The next piece is integration involving inverse trig functions. So inverse sine, inverse tangent, arcsine, arctangent. Remember, those are the same. And we talked about this, way back in Unit 3, maybe? But this table is kind of important, and I think they are things you need to kind of have memorized, which is not something I like to say, but it is the truth. So I'm sorry. And I want to go through an example with you. Specifically, we'll do at least 2 of these. We'll do the first one to start. So if we notice, I'm going to go back up, sorry, of course. If we notice here, we've got the basic forms of these integrals that the derivative of inverse sine is 1 over the square root of 1 minus x squared, which means the antiderivative of 1 over 1, the square root of 1 minus x squared is inverse sine. But if these pieces, 1 and x, are not 1 and x, that doesn't mean we can't do the problem. We can use u substitution essentially to still find the antiderivative by matching up the pieces with our equations. So for this first one, we have the integral of 1 over the square root of 4 minus x squared. Well, I look at this and I think the variable here, x, is, we're going to call that u in this case, and a, hold on, let me rewrite that. Instead of saying x is u, I'm going to say u is x. So if we notice, like, I'm looking at my variable here, and my coefficient, a, is, well, what's the square root of 4? It would be 2. Because again, if you look at all of these, we've got something squared. So I could really write this as the integral of 1 over the square root of a squared minus u squared. And the derivative of u is equal to the derivative of x, right? The derivative of u is equal to 1 dx, which means this dx up here, we can really write as du. And now, if we look over here, we see, hey, we're in our inverse trig realm. We have the square root of a squared minus u squared. So I know my integral is going to be inverse sine of u over a plus c, but of course u and a are not really the values we want here. Inverse sine of x over 2 plus c. Let's do another one. Maybe we'll just do b. So I look at b and I think, again, let's pick my pieces. My coefficient a, well, is really the square root of this value, so the square root of 2, and u is 3x, right? Because it would be 3x quantity squared, which means the derivative of u is 3 dx. So we plug our things back in. I'm going to make things smaller. Hold on. All right, we have to plug our pieces back in. So the integral of, instead of 1 over 2 plus 9x squared, I'm going to write this as the square root of 2 squared plus 3x squared. Well, actually, I guess I could do a and u, right? Because that's what we have defined as a and u. So it's a squared, because a is the square root of 2, plus u squared. And instead of dx, I really have 1/3 du. This coefficient we can pull out front. So we have 1/3 the integral of 1 over a squared plus u squared du. Take a moment, identify what we have. I'm seeing inverse tangent. So I have still this 1/3 out front times 1 over a inverse tangent of u over a plus c. But I don't want u and a. I'm going to plug back in the values I actually have, which this would be the square root of 2, 1 over 3 square root of 2 inverse tangent of 3x over the square root of 2 plus c. And even though we are very smart young people that would think we would want to rationalize this denominator, we actually don't need to. so I'm not going to do that. I want to talk to you guys about a very slightly different type of integration by substitution problem. So sometimes this is called the change of variable method, and it is U substitution, but it ends up being slightly different because we kind of play around with U and what we have here. So let's look at the first problem. X times the square root of 2x minus 1 dx. And I think to myself, well, if I pick the two things I could really pick for you are 2x minus 1 and x. And neither of those really does enough, right? The derivative of x is just 1. That's not going to cancel anything. The derivative of 2x minus 1 is 2. That doesn't really cancel anything either. But let's see what we can do if we just start by saying u is equal to 2x minus 1. And I know the derivative of u is equal to 2 dx. And the other piece I can do here is I can solve for x here. So u plus 1 divided by 2 is equal to x. Now trust me for a moment, if you will, on why this is important. So let's substitute our pieces back in. We have the antiderivative of, instead of x, I have u plus 1 divided by 2. Instead of the square root of 2x minus 1, I have the square root of u. And then I have times, instead of dx, I have du divided by 2. Let's do a little bit before we actually take the antiderivative. Notice this denominator and this denominator. Those are coefficients. We can pull those out front. So we really have 1/4 times the antiderivative of u plus 1 times the square root of u du. In this problem, this, my dear friends, is back to kind of where you started with integrals, where, okay, I know u, the square root of u is really u to the 1/2, and I'm going to distribute that. So I have 1/4 times the integral of u to the 3/2 plus u to the 1/2 du. Of course, I need more room. Well, what do we do with this integral? We calculate it like we've been doing, where we add 1 to our exponent and then divide by that exponent. So we have 1/4 still, to hold that out front. This would be 5/2, so that means 2/5 u to the 5/2, plus this would be 3/2, so 2/3 u to the 3/2, plus c still. And from here, I don't even really need or want to do that much more simplification. The only thing I am going to do is, instead of u's, I do want to substitute back in my x. So I'm going to write this as 1/4 times the quantity, 2/5 times, what was our x? 2x minus 1 to the 5/2 plus 2/3, excuse me, 2/3 times 2x minus 1 to the 3/2 plus c. And so the thing that happened differently this time is that our derivative didn't cancel, but we were able to change our values to all just be in terms of u, which made it an easier integral problem. I think for the good of your note-taking sanity, I'm going to stop here for today, and we'll just continue what we can on Thursday.